A shell and tube heat exchanger can carry hundreds of tubes, and every one of them ends in the same plate. Drill that plate from metal and put it in hot acid, and it slowly corrodes, distorts, and pulls away from the tubes until the joints weep. The gray disc turning here does the opposite. It anchors every tube in line, keeps two fluids apart, and shrugs off the heat and chemistry that eat metal away. What makes silicon carbide right for this job is the way it handles heat. Its thermal conductivity reaches as high as 120 watts per meter Kelvin, several times that of stainless steel. So heat passes through the plate instead of building up inside it. And because the plate and the tubes share the same low thermal expansion, near 4 parts per million per degree, they grow and shrink together, keeping the joints tight through every cycle. The fluids passing through are rarely clean. With a hardness above 2,500 on the Vickers scale, the bore of each hole resists the scale, fines, and solids that scour softer plates, so the openings hold their shape and the flow stays even. Backed by high flexural strength and very low creep, the plate carries the weight and pressure of a full tube bundle without sagging or drifting out of line. Then there is the chemistry. Dense silicon carbide is virtually inert to strong acids, caustics, and corrosive process streams that thin metal tube sheets over time, and it stays stable at temperatures far beyond where alloys soften. In a corrosive, high-temperature exchanger, that means the plate sealing the whole bundle is also the part least likely to fail. All of that is built into the bond. Silicon and carbon lock together through strong covalent links into a dense, almost diamond-like lattice, which is why the material is so hard, so chemically stable, and able to carry heat so well. The same tight network resists oxidation and holds its shape where metals would yield. How it is fired matters just as much. Pressureless sintered silicon carbide forms a fully dense, non-porous body, so the plate is impermeable from face to face. No path for one fluid to seep through to the other. That density is what lets a ceramic plate seal a pressurized bundle as reliably as it conducts heat. No two exchangers share a layout, so each tube sheet is made to the drawing. The disc diameter follows the shell, the thickness follows the pressure it must hold, and the hole pattern, its count, pitch, and bore, is matched exactly to the tube bundle. Every opening is ground to a tight tolerance so each tube seats square and seals clean. From there the details follow the design. Triangular or square hole pitch, chamfered or stepped bores for the sealing method, edge and groove features for gaskets or bonded joints, and a silicon carbide grade chosen for the duty. Whether the plate carries a handful of tubes or several hundred, it is cut from the drawing rather than a shelf. Nowhere does the tube sheet earn its place more than in a corrosive shell and tube exchanger. There, aggressive acids or hot process streams run through one side while a second fluid flows across the other, and the plate has to keep them apart at pressure, cycle after cycle. A silicon carbide tube sheet manages every front at once. It resists the acids that pit metal, it expands at the same rate as the silicon carbide tubes so the joints never loosen, and its hard, dense face shrugs off the erosion and fouling that block flow. Where a metal plate would corrode, distort, and start to leak, this one simply keeps the bundle sealed and the heat moving. Impressively, the heaviest, simplest looking part of the exchanger is the one quietly deciding how long the whole unit lasts.